Hello, Gen Chem Tribe. In this lecture, we're still talking about Gibbs free energy, but now getting into other methods to solve or use this idea of delta G. So we have this notion of delta G of reaction, and so far we have, one equation, which is the Gibbs free energy expression that we did an example of just recently. So this would be our Gibbs. But there are alternatives as well. We could also use delta G's of formation. And we can then also get a sense of the delta G of reaction using an equation that's very similar to our enthalpies and our entropies, by just looking at a difference in the delta G's in formation of our starting materials and our products. We have N here, which is stoichiometry. And so we then have the delta G of formation for our products minus the delta G of formation for our starting materials. And so we can get at a delta G from that angle as well. From the second equation, we really can't ascertain whether it's temperature or not temperature dependent. We could only ascertain that it is spontaneous or not spontaneous given the delta G's. So realize that both these equations sometimes can be utilized. One, just to figure out delta G as far as, equation 2. Equation 1, we can do that as well. But in terms of that spontaneity or temperature dependence with spontaneity, that's when we really need to know what delta H and delta S actually is. So, equation 2, right, just basically tells us if a process is spontaneous or not. It does not tell us if it is temperature dependent. Equation 1, right, does both. Meaning that it tells us whether a reaction is spontaneous or not. And B, tells us if it is a temperature dependent process. So, and that's what we're just getting from this idea of delta G's of formation versus delta G of reaction, delta H of reaction, and delta S of reaction. So in equation 2, we can just get at, the sign of delta G and whether it's spontaneous or not. With equation 1, that's what we need to to utilize if we're trying to figure out that temperature dependent part. So let's do an example putting these two equations basically together. So one method to actually reduce iron oxide or rust to iron is by reducing it with hydrogen gas. And so we can draw that reaction here. Here's our iron oxide, our hydrogen gas to produce solid iron, and then 4 H2Os in the gaseous state. So there's our reaction for the reduction of iron oxide. And so using delta G's of formation, determine whether this process is spontaneous or not. If it is non-spontaneous, is it temperature dependent? And then finally, if we are temperature dependent, at what temperature will the reaction become spontaneous? So there's our long drawn out question. We really have a number of parts that we need to figure out. We really have the top here, using our delta G's, this process is spontaneous, or not. And so that would be part A, and this is where we would be looking at the sums of our product minus the sum of our starting materials in terms of our delta G processes. So that would be part A. Part B, asking us, is it temperature dependent? That means we need to have some notion of delta H and delta S in order to determine whether it's temperature dependent. And then finally, asking the question of what temperature will the reaction become spontaneous, we could say that that's part C. And the only expression that we have that relates delta G to temperature is the Gibbs free energy expression. So that's how I would look at this question. It's just a kind of number of parts here, A, B, and C, but they're really talking about the two equations, really the, delta G of reaction from delta G's of formation, part A, and then part B and C are really talking about the same idea as far as this idea of the Gibbs free energy expression. With part B, we're looking for, this idea of driving forces. It's kind of the question mark. To determine whether it's temperature dependent or not, and then going to solve for the temperature if all this falls into place. So let's start with our part A. So basically we need to look up these delta G's of formation. We go up to our reaction. We would have to look at our products first. And so on that product side, we have 4 of these gaseous H2O molecules. And we have 1 in terms of our iron. I'm sorry, we're making 3 of those irons, so we'd have 3 times the delta G for our solid iron. There are our products, and now we're going to the starting materials, and so we would have 1 times the delta G for the iron oxide, plus then 4 times the delta G for our hydrogen gas. One thing to note, just like with delta H of formation, elements in their natural state have a delta G of formation equal to actually 0. So very similar to delta H in that respect, definitely opposite to that of entropy, right? Everything has entropy. That's our third law of thermodynamics. So now we're just basically going to tables to look up these particular values. So if we take and start to look these up, we would have the delta G for gaseous H2O would be negative 229 kilojoules per mole, plus 3 times 0. For our iron in its natural solid state, monoatomic, so it's 0. And then we can now go towards the starting materials. We look up rust or iron oxide, we get a negative 1013 kilojoules per mole. And then just like with the iron, the hydrogen in its natural state would be 0 kilojoules per mole. And so those are our starting materials. So our delta G of this reaction would be equal to 97 kilojoules per mole. And we would say that this is not spontaneous. So this is our answer for part A. And remember that these values that we got above here are just found in tables. So we're just plugging them in from tables, looking them up, making sure we have the right molecule, making sure we have the right phase of that molecule. Part B, question is now saying, okay, if, non-spontaneous, which it is not, is it temperature dependent. And what that is getting at is we need to know now the sign of delta H and delta S to basically determine the temperature dependence. So, I mean, there's a couple different ways that we could do this. We could just do enthalpies of formation, entropies of formation. I'm going to do a little bit differently than that. But so first with this, we're going to start with entropy. And so our entropy of the reaction would be much like what we see above, that we would have, 4 times the entropy for our gaseous H2O plus 3 times the entropy for our solid iron minus then the entropy of the iron oxide, and then 4 times the entropy of the hydrogen gas. And just like before, we're looking up these values, we're looking these up in actual tables. And so if we start to plug these in, we have a delta S of the reaction equal to 4 times the entropy for H2O gas, which is 189 joules per mole Kelvin, plus 3 times the iron, which is 27 joules per mole Kelvin, minus then our rust, which has a value of 146, plus then 4 times our hydrogen gas, which is 131 joules per mole Kelvin. So that means our entropy of the reaction would be equal to the sum of our products, which is 837 joules per mole Kelvin, minus our starting materials, which will be a total of 670 joules per mole Kelvin. And so that gives us a entropy, or delta S of reaction to be equal to 167 joules per mole Kelvin. So since we know that, right, a positive delta S of the reaction is a driving force. So, since the reaction is non-spontaneous, and we got that from part A, but the entropy of the reaction is positive, and remember that is a driving force. That means we have a temperature dependent process because of those features. So that was really kind of the answer to part B, right? Was, do we have a temperature dependent process? And we actually do at this point. Now let's take a look at our delta H value. For the delta H of reaction, we could use either our sum, using heats of formation, as far as our heats of formations of our products minus the heats of formation of our starting materials, or we could use Gibbs, or our delta G is equal to delta H minus T delta S for the reaction. And I'm going to choose Gibbs. So in getting at delta H, right, we have the delta G already, we have delta S already, and we know our temperature as well. There's no mention of temp in question, so we need to assume 298 Kelvin, or standard state. So if we go to our delta G, that was a 97 kilojoules per mole. That's equal to our enthalpy of reaction minus our temperature, which is the 298 Kelvin, times our entropy, which is 0.167 kilojoules per mole Kelvin. Again, be careful of units. In this case, I've converted to kilojoules. And we can see that with the kilojoule per mole idea with both the delta S as well as the delta G. And so I can quickly manipulate that and solve for our delta H of reaction to be 146.76 kilojoules per mole. So there is our delta H of reaction. And note that this is a positive delta H, and a positive delta H is not a driving force. So if entropy is positive Again, positive entropy is a driving force. So if entropy is positive and enthalpy is positive, right, a positive delta H of the reaction is not a driving force. Then we have a temperature dependent process. The higher the temperature, the more spontaneous the reaction becomes. So we know we're looking for a higher temperature than 298. So now we need to figure out how to actually, solve for what that specific temperature actually is. So this is really kind of getting to the last part of this, or part C, where we know reaction is non-spontaneous at 298. We know reaction is temperature dependent, and that was really parts A and B. And so now we're asking, what temp does the reaction become spontaneous? And so for that, we have to kind of go back to our Gibbs free energy expression, or really just Gibbs free energy in general, right? That if we have a delta G of the reaction that is greater than 0, well, this is positive, and this is non-spontaneous. If we have, though, a delta G that is negative or less than 0, now we have something spontaneous. So if we set our delta G of the reaction equal to 0, now we're on the cusp, between being spontaneous and non-spontaneous. So that's what we need to do, is use the Gibbs free energy equation again. Where now we're solving for our temperature. Our delta G of the reaction we're going to set to 0 kilojoules per mole, because that's the cusp. We have our delta H, which we solved for, is 146.76 kilojoules per mole. minus our temperature, which we're solving for, times then our entropy, which was a 0.167 kilojoules per mole Kelvin. So our temperature would be equal to our delta H. If I bring that over to the other side, I have a negative 146.76, and I divide over my negative 0.167 kilojoules per mole Kelvin. Our negative signs cancel out, which makes sense. We can't have a negative Kelvin, and we end up with a value of 878.8 Kelvin. Or if we converted it over, we would have 605.8 degrees Celsius. And so that is the temperature at which we need to get beyond. So this means that the reaction will become spontaneous once the temperature is greater than 878.8 Kelvin. And so there's bringing a lot of different things together, looking at delta G in a new light with, delta G's of formation, products minus starting materials. Again, reinforcing the idea of driving forces with entropy and enthalpy. And then in this example, finding that we do have a temperature-driven process, we can actually find the temperature at which we switch over between spontaneity and non-spontaneity. And that's just setting our delta G equal to 0.